So one of the things that we can now do with our information and understanding about state functions is to take a look at an observation that was made by Germain Hess a little bit over 100 years ago. And it's now called Hess's Law. The understanding behind Hess's Law is this. If we understand that enthalpy, H, is a state function, that means that it doesn't matter how you get from point A to point B, from start to finish. It just matters that you have a start and a finish and what the difference is between those. So delta H, the change in enthalpy, is path independent. It doesn't matter how you got from A to B. It just matters that you have a change in H. Because of that, that means that if you go from a set of reactants to a set of products, the total enthalpy change of that reaction is the same regardless of how many steps it takes to get to the products. If it's a one-step reaction or if it's a multi-step reaction, it doesn't matter. The overall energy change of that reaction is going to be the same. So visually it might look like this. If we want to take, for example, nitrogen and oxygen and produce NO2, well, what if that occurs by two steps? What if first we have to take the nitrogen and the oxygen and we have to combine to make one or two molecules of NO, and then take the NO and combine it with another oxygen to make NO2. Well, that takes a certain amount of energy to do that, but the overall difference in energy between the reactants and products is 68 kilojoules. What if it happens in one step? We just go directly. Well, it should still be 68 kilojoules. And it's essentially the difference between delta H2 and delta H3. Okay? So we're subtracting. So it doesn't really matter how many steps it takes to get from A to B. The overall energy from reactants to products is going to be the same. And that's essentially what Hess's Law says. So here's an example using the same value that we just had here. We know that N2 plus 2O2 goes to 2NO. If it's in one step, delta H is 68 kilojoules. If we do it by the two-step method, in other words, first we take nitrogen and oxygen, we make 2NO. The delta H for that is 180 kilojoules. And then we take those 2NO and we react it with another oxygen molecule and we get 2NO2. That's an exothermic reaction. That gives back 112. Well, we put those two together, delta H is still 68. It doesn't matter if we go by one step or a number of steps. So you might say, well, how do I know if it's one step or another or a number of steps? It doesn't really matter. You'll be able to figure out the overall change in enthalpy for a reaction using Hess's Law. Okay, there are some rules though. The first rule is if a reaction is reversed, for example, if you have to manipulate some of these equations, and you'll see what that looks like in just a second. If you do flip one around, you have to change the sign of delta H. The sign tells us the direction of heat flow at constant pressure. So if you have a reaction that is producing heat and then you flip it around, you reverse it, well then it has to absorb that amount of heat in order to go in, so it becomes endothermic. The size or magnitude of delta H is directly proportional to quantities of reactants and products. What does that mean? Well, that means that if you multiply a reaction by an integer, you have to multiply delta H as well by that same integer in order to keep the amount of energy consistent. Okay? Delta H is an extensive property, which means it depends on how much stuff you have. Here's an example. So we can do some data. We can get the enthalpy of combustion for graphite. In other words, if you combust graphite, you can use calorimetry to determine how much heat per mole is released. Now, you wouldn't use your simple calorimeter. You'd use a bomb calorimeter, but we can still do that. We can do the same thing with diamond. Most people don't realize diamonds burn. They form carbon dioxide and water just like anything else. So what we want to do is we want to use those two values. We want to find the delta H, the amount of energy change for the conversion of graphite to diamond. So is converting graphite to diamond, is that an endothermic or exothermic process, and by how much? That's what we're going to be doing here. So the first thing we need to do is we need to look at the equations. So here's the equation for the combustion of graphite. Okay, graphite plus oxygen goes to CO2. And delta H is negative 394 kilojoules per mole. Here's the second equation. This is for the combustion of diamond. Negative 396 kilojoules per mole. They're very close. The difference would lie in the fact that diamond is much more ordered, stronger bonds between the carbon atoms, and so it's going to take a little bit more energy. You're going to get a little bit more energy when you combust it because there's a little bit more energy holding it together. Okay? So to get to the desired equation, the equation we're trying to get to is graphite to diamond. We have to reverse the second equation because we need to get diamond on the other side. So The first one stays the same, but the second one gets reversed. And it gets reversed so that diamond is on the right side of the equation, on the right side of the arrow. Now, what we can do then is we can add up the two delta H's on that side, and we get a total of 2 kilojoules per mole. We can do that by crossing out anything that shows up on both sides of the equation. So the oxygen shows up on both sides, so we can cross that out. And the carbon dioxide shows up on both sides, so we can cross that out. And all that leaves us with is graphite to diamond. We add the two delta H's together, 394 plus 396, or negative 394 plus 396, and we get 2 kilojoules per mole. So delta H is 2 kilojoules per mole. In other words, you have to put some energy in to convert graphite into diamond. Okay? Here's a second example, and I want you to try this one. Okay? You're going to find the enthalpy change for the synthesis of diborane, B2H6. All right? This is the equation that you're going to try to get. 2B plus 3H2 goes to B2H6. Here are some fundamental equations that you can use. So here's the first one. This is the reaction of boron with oxygen to form B2O3. And there's your delta H value for that. Here's the value for B2H6 being combusted to B2O3 and H2O. There's your delta H value for that. And here's the value of hydrogen plus oxygen to water. Okay? So using that information, I want you to stop the video. And, oh, you need one more, sorry. H2O, liquid to gas. So if we want to boil water, we already know that's 44 kilojoules per mole. Stop the video and see if you can use these 4 equations to come up with the top equation, and then add up your delta H values and figure out the total heat of reaction. Okay, stop the video, try it out, and come back when you're done. All set? Well, let's see how you did. So here's your equation that we're going for. All right. We want to figure out what needs to go on the left and what needs to go on the right. So we need boron by itself, the solid boron on the left. We need hydrogen on the left. We need B2H6 on the right. That's all we need. So we're going to have to arrange our equations in such a way that we can cancel out what we don't want. Okay. The first equation that we can use, the boron plus oxygen going to B2O3, that has boron on the correct side. That has boron on the left. So we'll leave that alone. We won't reverse that or anything. We will reverse this equation, though, because this equation has B2H6, and it had it on the wrong side. We need to flip it around so B2H6 ends up in the product side. Okay, so we'll have to reverse that. And that means we change the sign of delta H. The third one can stay as is. And the reason we're going to keep it that way is because ultimately we're going to need to get rid of some water and some oxygen and things like that. But we want to have hydrogen stay on the left because we need hydrogen in our reactants, so we're going to keep that over there. And number 4 we'll keep as well so that we can cancel out some water. All right, so the only one we're reversing now is number 2. If we then go ahead and put those together and we underline what we want to keep. So I want to keep the boron, I want to keep the B2H6, and I want to keep CH2. Everything else I should be able somehow to cancel, depending on where it is, right? If it's on the right side or the left side. And remember, if they're on opposite sides of the equations, they can cancel. So I've got some B2O3 on both sides. I can cancel that out. I have 3H2O gas on the left side. I have 3H2O gas on the right side, so I can do that. I can cancel out some oxygen, and I can cancel out some B2O3. So I've got plenty of things that I can cancel. And here I've gone and done that. I've canceled out. Now, one of the things I had to do, though, was to get the number of hydrogens correct. I had to multiply equation number 3, which had H2 in it. I had to multiply that by 3 so that I could have my 3 hydrogens. And that means that I have to multiply the delta H for that equation by 3. I also needed 3 waters to cancel, so I had to multiply equation 4 by 3, and that means I also had to multiply its enthalpy by 3. Okay? So when I do all that, I cancel out the things that I don't need anymore, the B2O3. These lines are canceling aren't exactly matched up, but I think you can see where we need to cancel things out. And then I go ahead and add up the delta H's, negative 1273 plus negative of negative 2035, so that's a positive 2035, plus 3 times negative 286, plus 3 times 44. And when you do all the math, and this is the most important part of this calculation, be very careful of your negative signs and your positive signs. The arithmetic is where most people get screwed up here, so just be very careful of that. Okay? We should come out with 36 kilojoules when we're all done. All right? So there's not a whole lot to this as long as you have the fundamental equations. Now, what if you don't have the fundamental equations? What if you just have the reaction and you want to figure out its overall enthalpy? There's still a way to do that, and we'll see that in the next video. Okay? But for now, watch the video, go back, rewatch it, pause it, take good notes, and make sure you understand it. And if you don't, ask it in class.